So, we have looked at radiation generated from compact stars in their magnetospheres as well as through the release of trapped thermal energy. But a much richer set of phenomena occur in compact stars when material from surroundings or its companion star is accreted onto the surface, and this is of course known as accretion. Compact stars are particularly interesting from the point of view of accretion, because they provide a very large and deep potential well, gravitational potential well, in which the accreting matter can fall and thereby can get very bright. Most important class of systems in this class are compact stars in binary systems, where the compact star has a companion star which is not yet a compact star. So, it is a large loosely bound star from which the gravity of compact star can strip matter and accrete onto itself. The accretion process can be divided into two major classes, one in which the companion star is still a bit distant from the compact stars, so that the direct pulling of matter from the surface of the companion star to the compact star is not possible, but the companion star has winds like all stars do, as we know even the sun does. The wind of the companion star passes over the compact star and some part of the wind is captured. So, either that is a process by which the compact star gathers material that falls onto itself, or if the companion star is somewhat closer, then matter can be directly stripped from the surface of the companion star and brought to the surface of the compact star through what is called Roche lobe overflow. Now, this transfer of matter from one component to another actually profoundly affects the life of the binary system itself, including those of both of the stars. If the compact star in the binary system happens to be a white dwarf, then such a system is termed as cataclysmic variable. On the other hand, if the compact star which is accreting matter happens to be a neutron star, such an object is called an X-ray binary. We have seen rotation powered pulsars. Neutron stars with strong magnetic field which accrete matter can also produce emission which is periodic as seen by the observer, and such objects are called accretion powered pulsars. Because the gravitational potential on the surface of a neutron star is much larger than the gravitational potential on the surface of a white dwarf, the radiation emitted from a neutron star, to get to which matter has become now much hotter, is in X-rays, whereas those from the white dwarf tend to be in the optical region. Now, matter accreting onto a compact star can have a high fraction of its rest mass energy extracted into heat, and that is because of the large gravitational potential. So, this factor is called the efficiency factor eta and is written as g m over r c squared, where m is the mass of the compact star and r is its radius. So, for a given mass, if the radius is smaller, the eta is much larger. This eta happens to be about 10% for neutron stars or black holes, whereas it is a much smaller value of the order of 0.03% for white dwarfs. At this point, we can make a comparison with the amount of energy conversion, rest energy conversion in nuclear burning. Hydrogen burning into helium releases 0.7% of its rest energy into heat. Matter falling onto the surface of the white dwarf releases 0.03% of its rest energy into heat, whereas matter falling on the surface of a neutron star would release 10% of its rest energy into heat, which is much larger than what was ever possible from nuclear burning. Now, if the energy released is converted directly in one shot into thermal energy, then the temperature that this will correspond to can be extremely high. For material falling onto the surface of a neutron star, this would then correspond to a temperature of about 100 million electron volts. In practice, the energy is not released in one shot. The release is much more gradual. As the material approaches the compact object, already because of interaction among itself, the local friction and so on, it begins to release the gravitational energy into radiation already very far away from the compact object, and as a result the temperatures the accretion flow attains eventually is much lower than this one shot conversion that we are talking about. Now, maximum radiative luminosity of an object is given by the so called Eddington limit. This is a very simple expression where one has 4 pi gravitational constant times mu the mean molecular weight times proton mass times speed of light divided by Thomson cross section times the mass. So, this is more or less a combination of fundamental constants times mean molecular weight times the mass of the star. This has a figure of about 10 to the power of 38 ergs per second for 1 solar mass. Now, what does this mean? This means that if there is material surrounding the star which is producing this luminosity, then this radiation needs to pass through that material. The amount of momentum that this outgoing radiation will transfer to this surrounding material due to interaction of photons with matter is related to this Thomson scattering cross section, and this momentum transfer therefore produces a outward radiative force. Now, as the luminosity keeps increasing, the outward radiative force will also therefore increase. So, time will come when the inward gravitational force on a proton would be balanced by the outward radiative force on it because of outgoing radiation, and this balance is obtained at the Eddington limit, which means if the star is radiating at this rate, it is difficult for any further matter to fall onto the star. So, hence this limiting luminosity also leads to a limiting accretion rate, which is called the Eddington accretion rate, m dot Eddington, which is L Eddington divided by eta c squared, and that is about 10 to the power of 18 grams per second for 1 solar mass and radius of the size of neutron star. In fact, this quantity is a function only of the radius of the star. When all factors are put in here, one will find that the mass will cancel out. So, it just depends on the radius of the star. The smaller the radius, the smaller the Eddington accretion rate. If the external agents like the companion star and so on, if the external agent is trying to transfer matter to the compact object at a rate larger than m dot Eddington, then what would normally happen is a large fraction of this matter will actually not fall on the compact object, but will go out of the system. So, this will lead to some bloating envelope and lot of wind from the system, which will take the matter away. The matter coming from an external source like the compact object, as one has illustrated in this diagram, tends to approach the compact object in the form of an accretion disk. This accretion disk forms because matter leaving the companion star has an orbital angular momentum which is going around the compact object. Now, that angular momentum, if not reduced, will keep the matter spinning in an orbit around the compact object, and it will never reach the compact object. So, what happens is initially you would have this angular momentum, the matter will come round and the stream will strike itself and there will be an intersection point. At the intersection point there will be dissipation, and as dissipation occurs, the kinetic energy will be reduced and the frictional process will transport the angular momentum. Some of the matter will now have a lower angular momentum than it started with, and then with a lower angular momentum it will go then in a smaller orbit around the compact object. This process will continue until entire disk is formed, and it is from the inner edge of the accretion disk the matter will eventually then reach the compact object. So, this accretion disk is formed due to the self interaction of the accreting material. So, self interacting dissipative processes including viscosity and angular momentum then acts towards generating accretion disk profile. You start with some sharp distribution of matter over here, over time due to viscosity it then spreads over and an accretion disk is formed. The accretion disk, as it proceeds from outer region to inner regions, gets hot because of this dissipative processes, the friction that is transporting energy and angular momentum. As the disk gets hot, it begins to radiate locally. A steady situation occurs when you can consider each ring of the disk being in steady state equilibrium of the energy being generated within the ring due to friction and the energy being radiated out from the outer surface of those rings. And this then establishes accretion disk structure, thin accretion disk structure, where the angular velocity at any radius is given by the Keplerian angular velocity, and the accretion rate can then be written as the surface density of material at any radius times the twice by r the perimeter of that ring times the radial velocity, which is the inward velocity, that is the m dot, and that inward velocity is related to the viscous dissipation. So, this can be now related to the viscous torque, and going through now the algebra including the angular velocity and the rate of change of angular velocity and the viscous dissipation rate, one can obtain finally the distribution of temperature as a function of radius, and that distribution of temperature is plotted here. So, as the disk from outside comes nearer the compact object, the temperature keeps rising until you come to the inner truncation radius of the accretion disk. And the dependence of the temperature on the accretion rate is accretion rate to the power 1/4, and this is the dependence on radius. So, the accretion disk then becomes the main source of radiation around the compact object, and it does not matter if the compact object at r equal to 0 is itself radiating or not. A lot of radiation is generated by the matter in the process of approaching the compact object, and this is how we actually are able to observe systems which have black holes at the center as the compact object. The black hole itself has no radiation being produced, but the disk around it produces all the radiation that we see. Now, in a accreting binary system, if the compact object which is undergoing accretion, if it happens to be a white dwarf, we mentioned that such systems are called cataclysmic variables. They are called cataclysmic variables because from time to time they would undergo some massive explosion on the surface, and this explosion occurs because of the following. Let us say the companion star is supplying matter composed mostly of hydrogen and helium onto the surface of the white dwarf. The material accumulates on the surface of the white dwarf, and as it accumulates, as more and more matter arrives, this matter which has started coming in the beginning starts getting hotter and hotter. As the matter gets hot, at some point we reach a situation where nuclear burning can set in. So, nuclear fusion can set in. So, once a thermonuclear energy generation begins, as we have noted before, the energy per gram of material that is generated due to hydrogen burning is much larger than the binding energy of this material onto the white dwarf surface. So, once nuclear fusion begins, this nuclear fusion is going to dump a lot of energy in the matter being accreted, and this thermal energy will cause the envelope to be ejected with an explosion, and such explosions are called nova explosions. They are explosions, but they are not as energetic as the supernova explosions we talked about before. These are small explosions, but still quite spectacular explosions. So, these are called novae. In some cases, the explosions are avoided, but the envelope expands to a very large size, and one can get into a symbiotic kind of star, and those kind of systems from time to time will show the steady burning of hydrogen or helium on the surface of the white dwarf, and the spectrum of such objects extend to X-ray wavelengths, but to very soft part of the X-ray wavelengths, very low energy part of the X-ray wavelengths. So, they are called super soft sources. Now, if the white dwarf happens to have a strong magnetic field, then material coming from the companion object may directly get onto the magnetic field before forming an accretion disk. Such objects with strong magnetic fields in white dwarfs are called polars or intermediate polars, and these can produce radiation both due to the heated accreting matter as well as cyclotron resonance which happens in the magnetosphere. Now, all this accretion, if it happens to be in a situation where the material being accreted is not composed of hydrogen so much, but heavier elements, then the nuclear burning does not produce enough energy to lift the matter from the surface of the white dwarf. In that case, the mass of the white dwarf will grow with time. As the mass of the white dwarf grows with time, at some point the white dwarf mass may reach the limiting mass. If the limiting mass or Chandrasekhar mass is reached, then any further addition to mass of that white dwarf will then trigger a quick collapse of the white dwarf. Now, in this case, as the collapse proceeds, there will be a large amount of heating that will occur because of the gravitational mining energy that is released. Now, the white dwarf is still made of material which is in principle combustible. It is not made up of iron, but it is made up of either carbon, oxygen or oxygen, neon, magnesium and so on. So, this heating which is going to be caused by the gravitational mining energy released in the collapse at some point will ignite the material or drive it to nuclear fusion, and this nuclear fusion will explosively burn the entire white dwarf and cause an explosion which is like a supernova explosion, leaving nothing behind. So, this is another type of supernova explosion which is caused not by the collapse of a massive star's core, but by accretion onto a white dwarf, and they are called supernovae of type 1a. Coming now to the accretion onto neutron stars. Here again accretion disk forms around the neutron star, material approaches the neutron star, and at some point the material gets on to the magnetic field. So, accretion disk gets truncated, material then gets onto the magnetic field and follows the magnetic field, arriving at the neutron star surface at two hot spots corresponding to the two magnetic poles. This neutron star, if it now rotates around an axis which is not aligned with the magnetic axis, will present to the viewer a varying intensity of X-rays coming from these hot spots. So, the hot spots will come into view and go out of view and so on. So, that is what causes a periodic X-ray intensity variation, and we call them accretion powered pulsars. Apart from this periodic modulation of intensity, which is seen in some cases, not seen in all cases. In fact, for a tight collimation of matter to happen to arrive at the pole to create a small hot spot requires a fairly strong magnetic field above 10 to the power of 9 Gauss or so. So, if the field is not that strong, the matter arrives with a much larger swath on the surface of the star, and this contrast of hot spot and the rest of the star is reduced considerably. One is not able to see the pulsations that well. But in addition to this pulsar kind of periodic structure in the temporal intensity variations, there are also many other complex structures that are seen in the X-ray intensity variations of these objects. In particular, kilohertz quasi periodic oscillations are a very important signature of the inner edge of the accretion disk. Typically, these frequencies are related to the Keplerian frequency at the inner edge of the accretion disk. So, if in the Fourier spectrum of the intensity fluctuation such features can be identified, then one can estimate how close to the neutron star the accretion disk actually extends, and as a result sometimes this can be used also to place constraints on the radius of the neutron star itself, because the inner edge of the accretion disk must at least be larger than the radius of the star. Now, as we saw, the accretion disk is truncated at some point because of the interaction with the magnetic field. Now, this interaction not only truncates the accretion disk, but also through the magnetic field connects the rotation of the central object with the Keplerian motion of the accretion disk. If at the point of this magnetic connection the accretion disk is rotating faster than the central object, then a rotational stress is transmitted through the magnetic field to the star from the accretion disk, and this rotational stress will tend to spin the central object to faster and faster periods. So, this is the spin up process by which a slow rotating neutron star by accretion can be converted to a very fast rotating neutron star. On the other hand, if at this point of magnetic connection the accretion disk is spinning slower than the neutron star, then again there is a rotational stress that is transmitted through the magnetic field, and angular momentum is extracted from the central object to the accretion disk, and by which material can fly off the accretion disk by due to the addition of this extra angular momentum. So, you can get what is commonly known as the propeller effect, which inhibits accretion and extracts angular momentum from the compact star, thereby slowing the neutron star down. The relative value of the spin rate of the neutron star and the inner edge of the accretion disk of course depends on how close the accretion disk is to the neutron star. As we know from Keplerian motion, the smaller an orbit, the faster is the Keplerian rotation. So, the closer the disk approaches the neutron star, the faster will be the accretion disk rotation. Now, the stronger the magnetic field of the neutron star, the further away the disk will be halted. So, the approach to the neutron star, a closer approach to the neutron star requires a smaller magnetic field. So, if at equilibrium we consider that the inner edge of the accretion disk is spinning at the same rate as the neutron star itself, then that equilibrium period is shorter if the magnetic field is smaller. If the magnetic field is larger, that equilibrium spin equilibrium period is larger. So, in fact, that relation is captured here. Equilibrium period is proportional to the magnetic field to the power of 6 by 7 times accretion rate to the power of minus 3/7, because the larger the accretion rate, the closer the disk can proceed. So, for a given magnetic field strength, if the accretion rate is low, then the disk will be further away and it will cause a spin down. But if the accretion rate goes up, the disk will come in closer to the star and it will spin it up. Similarly, as the magnetic field goes down, the spin up will increase. Now, this is the root cause of the millisecond pulsars that we see, which have ended up here. They have all been processed in binary systems. Most of them still have their binary companions, which we can see. So, one expects that all these neutron stars were born as regular pulsars at some point in their life initially, and they went through their pulsar phase and they spun down, went into the graveyard, stopped functioning as a pulsar. Over time, either due to spontaneous ohmic processes or due to processes activated by accretion on the surface, their magnetic field decreased from the original 10 to the power of 12 Gauss or thereabouts to much lower values, which is about 10 to the power of 8 Gauss. When the magnetic field is low, the binary companion, as it started transferring matter, the low magnetic field allowed the accretion disk to come very close to the surface of the neutron star and thereby spin up the neutron star to very, very short periods of the order of a millisecond or so. So, this is thought to be the history of production of these millisecond pulsars, and now there have been objects which have also been observed, which are not just the end state, but also in the process of doing so. Now, we saw this large number of pulsars in binary systems. Those pulsars have gone through a binary evolutionary history, and then accretion has stopped, and now you have a pulsar and the remnant of the star which was donating mass, and the remnant of the star which was donating mass eventually can be a white dwarf if the donor star was of relatively smaller mass, or it could be a neutron star if the donor star was a somewhat higher mass, was of somewhat higher mass. There are a number of systems where we do know that the pulsar has a neutron star as its binary companion, and then there are some other cases where we know the neutron star has a white dwarf as a binary companion. Now, tight binaries of double neutron stars or tight binaries of neutron star or and a heavy white dwarf are extremely useful for certain measurements, and these happen to be the measurement of the orbital parameters of the binary system and their relativistic parameters, using which one can make an accurate estimate of the masses of the components in this binary system. In general, for a relativistic binary, that means binary systems for which relativistic parameters can be measured. So, a neutron star in a binary, one can measure the Keplerian parameters of the orbit, which was the binary period, the eccentricity, and the longitude of periastron. And we can also measure post Keplerian parameters in this case, where we can find the rate of change of orbital period as a function of time because of gravitational radiation from the system, the rate of change of longitude of periastron, which is the precession of the orbit due to relativistic effects, this quantity gamma, which is called the Einstein delay, and that is a combination of transverse Doppler shift and gravitational redshift in the system. Then the Romer delay, which is the propagation delay in the binary system, and S is the Shapiro delay, which is the excess delay that is caused by the photons from the pulsar propagating in the gravitational field of the companion. As it comes close to the companion, the photon trajectories have to traverse a larger gravitational potential well, and hence they get delayed additionally. So, all these quantities can in principle be measured, and through these measurements one can accurately measure the mass of both the pulsar and its companion object. And this has been extremely useful in trying to constrain the equation of state of neutron stars. This is a compendium of measured masses of neutron stars from various techniques, including the relativistic binaries that I talked about, and the best measured relativistic binary measurement is over here among the highest mass neutron stars. So, this is the largest mass which has been measured with a smallest error bar. The mass happens to be just around 2 solar mass. This actually does put constraints on what equation of state is allowed and what is not. In this diagram are shown several equations of state proposed from various kinds of extrapolation from laboratory data as well as theoretical predictions. The diagram shows the mass radius relation as predicted by all these equations of state. The horizontal lines show the measured masses of a few systems, and it is clear that some of the predictions in this table have their maximum mass below these measured masses. There are several other equations of state which did exist before these mass measurements took place, which have not been plotted here. But clearly this just the measurement of mass alone is able to narrow down the range of equations of state that are currently consistent with these measurements. Now, suppose tomorrow we have another mass measurement which is way up here, then many of these other equations of state where the maximum mass does not reach that value will get ruled out. So, accurate mass measurement is an important discriminator of equation of state. However, it will still allow a whole bunch of equation of state which actually crosses that mass measurement to be present. To do any better, one needs to constrain not only the mass, but also the radius or some other measurable parameter which is a combination of mass and radius. And this is what neutron star physicists are trying to do through measurements. Considering mass and radius, one of the techniques that has been used is thermonuclear X-ray bursts, where analogous to the nova explosion on white dwarfs, material accumulating on the surface of neutron stars would also undergo thermonuclear instabilities from time to time, and there will be a little X-ray burst that will be accompanied by it. Except in this case, since the binding energy is much larger than the amount of energy that the nuclear fusion can produce, the material will not eventually leave the system. It will expand and then fall back onto the surface. The maximum luminosity that one can generate in this process is clearly the local Eddington luminosity. So, now for a burst of this kind, through the burst, as you can see, there is X-ray intensity which rises and falls over time scales of a few seconds here. This entire diagram is 20 seconds long. But with a good measurement, one can find the luminosity as a function of time, the temperature, the black body temperature as a function of time, and through this one can connect the luminosity as well as the black body radius. X-ray flux divided by sigma t to the power of 4 is related to r squared, where r is the effective emitting radius, d is the distance to the star, Fc is a correction factor, because these X-ray measurements happen over a certain limited band of frequencies, but the actual radiation occupies a much larger range of wavelengths. So, to correct for that, we have a correction factor over here, and then this is the standard expression for gravitational redshift from the surface of the star and so on. So, we have at maximum the luminosity related to the Eddington luminosity, and once the burst occurs and then material settles down, the radius as derived from the luminosity and temperature, it initially rises as the material expands from the surface, and then it settles down, and as it settles down to a steady value, that radius can be attributed to the radius of the neutron star. So, if these measurements were error free, then this is a very good way to constrain the equation of state of neutron stars. Unfortunately, there are various uncertainties, including this correction factor that I talked about, because the spectrum does not look exactly like a black body. So, therefore, there are uncertainties in this correction factor, as well as uncertainties about whether the entire surface is involved in this thermonuclear X-ray burst or a portion of the surface, in which case a correction for that also is required, and that correction is somewhat unknown. So, in the end, folding in all those uncertainties, if one looks at what kind of constraint on mass and radius that these observations can put, they do put significant constraints, but it is still not good enough yet to single out one equation of state, but it is consistent with a certain band of equations of state. Finally, there is another important technique which is being applied to X-ray observations, and that is the pulse profile of X-ray pulsars. If there is a small hot spot on the surface of a neutron star, the pulse profile that an observer will see from a rotating neutron star with such a hot spot is given by this. Now, there are certain effects which are important for neutron stars, which includes the Doppler shift, because neutron star spins quite fast, the gravitational redshift, and the bending of light due to strong gravity of the neutron star. So, these effects, when you put together, there is a phase difference that is expected between the temperature measurement, which is shown as color here, and the flux measurement. So, the minimum of the temperature measurement will not be exactly at the same time as the minimum of the flux measurement, and vice versa. So, this phase difference between the color curve and the intensity curve is in fact an indicator of the mass and radius of the neutron star. This is a computation of what is expected for a spin rate of 600 hertz. The phase difference between the color curve and the intensity curve for different values of mass and radius. So, if this can be measured accurately, it will be a very good constraint on the mass and radius of the neutron star, and hence on the neutron star equation of state. This has been taken up very seriously, and in fact, one whole space mission called NICER, stands for Neutron Star Internal Composition Explorer. It is a payload which has been built and launched by NASA and installed on the International Space Station. It is currently collecting observations, and its primary purpose is to exploit this measurement, the X-ray pulse profile measurements of pulsars, to derive constraints on the equation of state of neutron stars. Another very new window that is looking quite promising to provide constraints on the neutron star equation of state is gravitational waves. We already talked about double neutron star binaries. We also mentioned that such binaries have a rate of change of their orbital period because of gravitational radiation that takes away energy from the system. As the system evolves under the influence of these gravitational waves, the orbit will become smaller and smaller and smaller as the energy continues to get carried away. Eventually, a time will come when these two neutron stars will merge. Leading up to that merger, the intensity of the gravitational wave emission will go up dramatically, but as the orbital period is also changing, the frequency of the gravitational wave will also keep going up. The laser interferometric gravitational wave observatories, LIGO, as well as other similar observatories like Virgo and Tama, have been built to detect signals like this, where two compact objects come close together and proceed to merger. So, this waveform in this diagram is drawn for 2 point masses coming closer and closer together due to gravitational wave emission and then eventually merging. Neutron stars, however, cannot be considered just point masses. Yes, when they are very far away from each other, their point mass is a very good approximation for computing gravitational waveform. However, when they come close together, the gravity of each other is going to distort both of these neutron stars, and that star, which is slightly loosely bound compared to the other one because of mass asymmetry, will get tidally disrupted first, material will go around it, and eventually it will form disc like envelope, and finally within this the merger will occur. So, this scenario, when they are very close together with material being stripped from one and finally merging, is very far from a description that can be obtained from point mass description. Because of this material stripping, the deformation and so on, this waveform is no longer the correct waveform very close to the merger. So, there are departures from such a waveform which will occur as is shown here between the dashed line and the solid line. This departure is caused by tidal deformation of the neutron star. However, the amount of tidal deformation a neutron star can undergo depends very much on the pressure density relation that constitutes the neutron star itself. So, the tidal deformability of a neutron star is a very good indicator of its equation of state. So, if by looking at the waveform of the gravitational waves coming from this merging system, if one can determine the tidal deformability of neutron stars, then that would produce a very good constraint on neutron star equation of state. So far, there has been only one report of binary neutron star merger having been detected in gravitational wave radiation, but there will certainly be more in the time to come. But even for that one object, this approach has been tried in earnest and has given interesting constraints, as I will describe presently. But before I do that, just define the tidal deformability. If the tidal potential, which is deforming a body, is imposed and is called U tidal, it can be expanded in multiple expansions in the spherical harmonics with these coefficients ELM, and this tidal potential causes a deformation of the object, and the deformation being described by this quantities ILM. Then hydrostatic equilibrium will demand that there is a relation between the two. In Newtonian description, this relation is described by this equation, where the ILM and the epsilon LM are related by this quantity KL, which is called a tidal love number, and this KL is a function of the equation of state that the body is built out of. There is also another quantity, tidal deformability lambda, that is often used in the literature here, which is actually a renormalized value of this tidal love number k. So, this is a Newtonian description. A very similar definition also arises in general relativity, which is appropriate for neutron stars. So, these are the tidal deformabilities or tidal love numbers for a whole bunch of equations of state as a function of m over r, and a whole bunch of equations of state which are listed here, for which this has been computed, and this can then be compared with what is observed, and thereby you can constrain which of these follow the pattern and which do not. Now, this is the constraint based on this one observation of 17th August 2017, where gravitational waves from this double neutron star binary merger was detected. The analysis of the data of the tidal deformability then constrains the mass and radius of the neutron stars within these regions. And the predictions from different equations of state, a few of them are shown here, and clearly the dark shaded regions are the highest probability regions, and this selects a smaller band of equations of state which are more consistent with the data than some others, and some others are really completely ruled out. So, this type of measurements with more such events to be detected in the future is going to provide further constraints on neutron star equation of state and take us closer to the understanding of the nuclear forces and fundamental physics that we are dealing with. And this shows the measurements derived from that one event of binary neutron star merger on 17th August 2017 detection. Measurements of the waveform and the consequent constraints on the tidal deformability have been translated to constraints on mass and radius in these diagrams, and the highest shaded regions, the dark shaded regions correspond to the highest probability. Clearly, these regions select some of the equations of state for which the mass radius relation as shown in this diagram pass through these regions, and some of the predictions of different equations of state are almost completely ruled out. Although this still leaves a fairly large band of equations of state still consistent with these present measurements. Over time, with more such events accumulated, this is looking like a very promising technique to provide strong constraints on the neutron star equation of state. Techniques like these, as well as other measurements which I alluded to in previous slides, and even a few other new techniques which are being resorted to now, is taking us towards better and better constraints on the neutron star equation of state, and as a result on the nature of the strong interaction itself, and helping us decipher fundamental physics based on astrophysical measurements.